All right, so as we move into the final chapter of the analysis book, the final chapter of analysis in this book, not the final chapter of analysis as a field, it started to become apparent in the 19th century, that is the 1800s, and even before that, that the mathematics that had kind of been rapidly developed in the century before by Newton, by Leibniz, and all of these other people that we had discussed, this was going to have to be taught to other people. And it's just sort of a feature of this course, or maybe not a feature, it's just a fact of this course, that the way that we have sort of organized, or not we, I should say the way that I have organized, which is, to follow other people's organization, but I sort of picked the books because I guess I was drawn to it, is that we kind of follow this path of great men, or great people. Okay, so this is not a people's history of mathematics. That would be a very interesting book to write, I think. But notice that even from the very beginnings, the people who were doing mathematics were not just ordinary people. The people doing mathematics had some position of power and privilege in some way, whether they were religious leaders or during the time when we started out, sort of political leaders would be similar, or whatever. It wasn't just ordinary people. It was always sort of the people who had a lot of leisure time, and then, of course, the people who are also very talented at it. But as we move along, more and more people have to learn mathematics. And now we are at a point where calculus, at least in the United States, calculus is a class that is regularly taught in high school, and not just to the brightest of the brightest, but to everybody. I mean, I'm obviously good at math now, and maybe in some sense I'm above average in terms of talent. But when I was in high school, that was not the case. I was a horrible high school student, and even I took calculus. I didn't understand any of it. I'm not sure the teacher understood much of it. But the point is, once we are in the early 20th century, the early 21st century, which is when I took math, which is when I was in high school. Even these people, even sort of the most mediocre of high school students are learning calculus. And this was a difficult transition to go through. Because again, as one of the challenging parts about teaching this course has been that I've had to sort of go back to thinking about mathematics the way people thought about it before we had all of this machinery developed. And that's been a challenge for me. And I think it's been a challenge for many of you. At least, I mean, not in a bad way, but in a good way. It challenges us to sort of think about things. Okay, so then what has happened, we have to have a more streamlined way for explaining this. I think we see this now with calculus, like the way that we teach calculus now is not really how it was historically developed. When we teach calculus now, it's like we can take a step back from how everything was developed and really decide, okay, we think this is the best way to teach it. It's just not taught the way that it was historically developed. At least most of the time, it's not taught the way that it was historically developed. It's more taught the way sort of that Cauchy has developed calculus. The other thing that I want to mention is that this hasn't happened to differential equations. Differential equations somehow has missed this, and really what happens, I think, in differential equations is that we really almost do sort of rehearse the entire development of differential equations. We add some things here and there, existence and uniqueness theorems that were not, part of the initial development, but it still is sort of the class seems to be just an ad hoc collection of tricks for solving different differential equations. And in my opinion, I would be happy, if there's discussion on this. In my opinion, there hasn't been this development, pedagogically speaking, like there has with calculus. I've tried this a few times in differential equations classes that I've taught. There are practical problems with this for a number of reasons. Anyways, so while that's going on, there's also, I think maybe we have Cauchy to thank for this, as he's trying to come up with lectures to teach. He's kind of realizing that there is this lack in rigor, that he's just saying things, he's teaching things, and he's maybe uncomfortable saying these things because there, like I said, there's a lack of rigor in why these things are true. Why is what he's saying true? And so he's wanting to introduce more rigor. And so we're going to cover many people whose names start to become more and more familiar. Cauchy, Riemann, Dirichlet, Fourier, Dedekind, Cantor, all of these people are sort of names that are involved with this program. Okay, and we're not going to talk about all of these people, but we're going to talk about some of these people. Okay, so one of the textbooks that was written to accomplish some of these goals that we're talking about was by LaCroix. I don't know if this has any relation to the water, or if they're even spelled the same name. That just thought came into my mind, and since I'm just talking to a computer screen, sometimes those thoughts come out. His textbook is based on the elementary notion of limit, but it was still heavy on series. So the translators at Cambridge, which you can look in the text for who those are, but these are again big name people, they did not like this, and they preferred the Lagrangian method of series. So Lagrange kind of based all of his calculus concepts and ideas on series. Let's expand a function as a Taylor series, and then let's analyze that Taylor series, and whatever it is we want to do calculus-wise, we're just going to do it that series. Now, that's a very attractive point of view for a number of reasons. One, it's essentially an infinite degree polynomial. Now, I know that's not technically correct, but in terms of algebraic manipulations, it's very nice. Polynomials are very well understood, so an infinite degree polynomial is also seemingly very well understood. You can sort of define what the derivative is. The derivative is the first derivative is the coefficient on the x term, or the x minus x naught term, however you want to call it, in a series. And then you have similar formulas, Taylor's formula for the coefficients of a Taylor series. You can have higher order derivatives defined defined in the same way. And then now the problem is, how do you come up with series? Well, there's issues with this. I mean, number one, even if you want to do calculus, not all differentiable functions have a second derivative. Not all differentiable functions have a second derivative, right? So what this means right away is that not all of the functions that you want to study are even going to have a series to begin with. Another issue, of course, which I don't, this was not something that they had I don't know the extent to which they had this in mind. It definitely came up in the 19th century. What about functions that are infinitely differentiable but are not equal to the Taylor series? This is one of the homework problems that we looked at last week. Show that e to the minus 1 over x squared, that you can't study that really using Taylor series, or Maclaurin series at least. Okay, so what about functions like that? So the Lagrangian method has a lot of good things. There's a lot of good things about it, but it's not sufficient for what needs to happen. And Cauchy did not like this lack of rigor. Okay. So what we get with Cauchy is we begin to get, I'm going to say, we don't quite get the modern notion of limit. Not quite yet, okay, with Cauchy. But we get something much closer to the idea of a limit than we had before. Okay, so we're not quite there, and I want you guys to think about why maybe I'm saying we're not quite there yet. So what he says is the following. I'm just going to read this. If the successive values attributed to the same variable approach indefinitely a fixed value, such that they finally differ from it by as little as one wishes, this latter is called the limit of all the others. Okay, now this is very similar to how we would say this nowadays. I can make, if I say the limit as x approaches a of f of x is equal to L, the sort of the words way of saying this is to say that I can make f of x as close to L as I want by taking x sufficiently close to a. I can make f of x arbitrarily close to L by taking x sufficiently close to a. That's sort of the words way of describing the limit. Now, the issue here is that that's a good limit. That's a good definition. But as we will see later on, it's not precise enough, and because of that, it's going to lead Cauchy to make a huge error. Now, I'm not saying he should be embarrassed by that. He's done so many things. We saw how Leibniz made an error with the product rule. I probably made that error with the product rule when I was first learning calculus. So I'm not saying this to to embarrass Cauchy. I'm just saying that even though he made a huge stride to what the definition of a limit should be, even with him, who was sort of obsessed with rigor and precision, this lack of precision here sort of led to a mistake. But one of his biggest contributions, which I don't think the book discusses enough, is that we go from a system where we're only dealing with equalities to a system where we're now dealing with inequalities. And this is a huge game changer, going from only having equal signs to having inequalities. So for example, let me just give one example of what I mean by this. So if we sort of think about just let's look at something like the differential, the product rule. If we have d xy like this, this would be equal to xy minus x plus delta x, x plus dx, y plus dy. And now after we do the various algebra things that we need to do, we're going to get that this is equal to, I did this the wrong way around, x plus dx, y plus dy minus xy. And again, after we do various algebra things, we're going to get x dy plus y dx, and then we're going to get plus dx dy. Okay, and now what we have to do is we just have to say, well, this is equal to 0 because if dx and dy are small. This is like negligible for dy and dx. Now there's ways, and we might see some of this in the next couple of weeks. There's kind of ways to make this, make these equalities make a little more sense. Okay. But from an analysis point of view, this is imprecise. There's a lack of precision and rigor here that needs to be addressed. And this is exactly what Cauchy is going to do. Because really what is said in a statement like this is that if we start with deltas, like if we say dx is going to be equal to like the limit and all of these d's are replaced with deltas, what we're saying is that this is going to 0 much faster than these others in a quantitative sense. Like this divided by that would go to 0. And so this is what Cauchy begins to introduce to us. So I'm just going to explain this. With one example here. So what he proves is the following. Now I'm going to use this limit notation. But what he proves is the following. He proves that if the limit, let me make sure I'm all on the board here, as x goes to infinity of f of x plus 1 minus f of x, is if this is equal to L, then this means that the limit as x goes to infinity of f of x over x is also equal to L. Okay, let me just make sure that I wrote this down correctly. Yeah. Okay, so this is what he proves. Okay, so why is this true, and where does this idea of inequality comes from? Okay, so sorry, I had a phone call and I'm not exactly sure where I left off, but this is what I'm proving. Okay, so like I said, the idea is that Cauchy introduces the notion, or not introduces, but Cauchy uses inequalities to prove this, that if the limit of f of x plus 1 minus f of x is equal to L, as x goes to infinity, then so is the limit of f of x over x. That's also equal to L. Okay, so what he does is the following. Here's sort of the principal place where the inequality is introduced. He says, okay, for x greater than, let's say, some natural number m, for x greater than some natural number m, we know, sorry, let me just make sure that I'm writing on the board. Okay. We know that L minus epsilon is less than f of x plus 1 minus f of x, and this is less than L plus epsilon. Now, really what we need to do here is we need to add an absolute value, because of course L minus epsilon and L plus epsilon, if L is positive and epsilon is small, they're both going to be positive. So we should really be dealing with absolute values, something like this. Okay, but now notice what he can do. He can make the following assertion. He can show we can determine something about f of m plus k minus f of k. Okay, so why is that? Well, we can write this in the following way. I'm going to write this in sigma notation, but this is just going to be a telescoping sum. We can write this as the sum. Sorry, this should be f of m here. We can write this as the sum from L equals 0 to k minus 1 f of m plus L plus 1 minus f of m plus L. Okay, and again, this is a telescoping sum that's going to be equal to this. Okay, now notice what's going to happen here. If I just think in terms of absolute values, f of m plus k minus f of k, I can come in here. Is now going to be less than if I bring in absolute values like this. And now this, each one of the absolute values of these terms is less than L plus epsilon. And so this is going to be less than or equal to, there's k terms, k times L plus epsilon. Okay, just using telescoping series. Okay, so I'm going to replace this sum with k. It's not telescoping series, but a telescoping sum. This is going to be less than or equal to k times L plus epsilon. Okay, now I can divide both sides by k. And we get that this is less than or equal to k plus epsilon. Really, there's a strict inequality here, so there should be a strict inequality here as well. It doesn't matter to the overall proof, but let me just put it like this. Okay, so now what we want to do, we want to make the change of variables for m plus k. We want m plus k to be equal to x. And so now it's not going to be so important that m is a natural number. And in fact, to make this make sense, we need it to be any number. So this is going to be x. K is now going to be equal to x minus m, because x is equal to m plus k, so x minus m is going to be equal to k. So this is what we have here. And now I can multiply both sides by x minus m. So notice what happens when I multiply both sides by x minus m. It comes back over here. Okay, so really I just divided by k, changed it, and then multiplied it back. So I guess it might have been more efficient to keep it over here, but whatever. Okay, so now this is what we have. Now one way, and keep in mind that x minus m is positive. Now what we're saying is f of x minus f of m, the absolute value of f of x minus f of m is less than L plus epsilon times x minus m. Now notice what's going to happen here. If I now divide both sides by x, I'm going to divide this term by x. I'm going to divide this term by x. When I divide this term by x, it becomes 1 minus m over x. Like this. Now here is the argument that Cauchy made at this point. So let me just say, for x greater than m, we had everything, and now what this is saying is that this is true. Again, x has to be greater than m. So I'm going to erase that top line. X is still greater than m, but the context has changed a little bit. So here's what Cauchy says. M is fixed. So as x gets bigger and bigger and bigger, this term goes to 0. And this term goes to 0. So in other words, by taking x sufficiently large, we can say that f of x divided by x, the absolute value of f of x divided by x, is going to be less than L plus epsilon, plus an error term. Then that error term goes to infinity. Okay, that error term goes to 0. So essentially, what he's proving here is that the limit as x goes to positive infinity of f of x over x, at least in absolute value, that's the way that I've explained it here, is less than L plus epsilon. And this is true for all epsilon. So what it says is that this is that, and then the corresponding negative inequality would be like this. Okay, so this is what it would be. And so now what he's saying is that this is true for all epsilon. And so we can make epsilon arbitrarily small, and so it means the limit of x, the limit of f of x over x as x goes to infinity has to be equal to L. And this is a very common way of proving inequalities. In fact, this is a very common way nowadays of proving inequalities. So, or proving equalities, because inequalities are typically easier to work with. So I would assume many of you are familiar with a prominent mathematician named Terry Tao. He has a book called An Epsilon of Room. Now, the reason he's doing this is because typically, if you want to prove two things are equal to each other, if I want to prove that quantity A is equal to quantity B, it's typically easier to prove something like A is less than B plus epsilon, and B is less than A plus epsilon, or something like that. That's typically an easier thing to prove. And that's exactly the task, that's exactly what Cauchy has done here. He says this limit is less than L plus epsilon, and greater than L minus epsilon. And since epsilon can be any number, it implies that this limit is in fact equal to L. So that's what Cauchy did. So the introduction of inequalities to analysis was a very important introduction. It's important because it is more precise than using equality. So at first that might seem counterintuitive that using inequalities is more precise than equality, because equality we're saying two things are exactly equal, whereas inequality that's not what we're saying. We're just saying there's like an order relationship. One is less than the other one. We don't know how much less it is than the other one. But the idea here is that if we prove two inequalities, one inequality on both sides, this is more precise, and then there's some sort of procedure, like I said, where if it's true for all epsilon, there's some parameter like that. We can then show that we can sort of make these inequalities arbitrarily precise. Okay, so again, it's a little counterintuitive to say that it is more precise to use inequalities rather than equalities, but the reason it's more precise is because the equalities don't actually exist in the arguments. It's inequalities in the argument. So using them, we're just simply using what is actually true rather than a less precise statement that is not true. Okay. So the last thing, actually, I'm gonna stop here, and I'm gonna make the next video. I'm gonna talk about Cauchy and continuity and the error that he